So we're studying now in Chapter 6 Maxwell's equations and radiation. And so you should be able to write down the full Maxwell's equations, the Lorentz force, as well as the charge continuity equation. In other words, the conservation of charge. Be able to write those down in terms of E, B, rho, and J. Okay, and also then the relationship between phi and A and the E and B fields. And in addition, he discusses a condition on determining phi and A from rho and J. So we also have rho and J. You can either write phi and A or E and B from rho and J. The expressions for E and B from the sources kind of complicated and was actually only recently published, oddly enough. But partly because they're complicated, I suppose. So what I'd like to look at now is the relationship between phi and J, phi and A, and rho and J, and also the equations for E and B. So you'll read in the text that away from the source, in other words, in the source-free region, that E, B, phi, and A all satisfy the wave equation. And so we're going to study the wave equation as a mathematical formalism. So I'll first write down the form of the wave equation, and I guess we'll write it down in this form. In particular, you find, for example, that phi satisfies this equation even with the presence of rho. And the same equation, a similar equation, is satisfied by A in the presence of J. So where rho and J are equal to 0, you have this form, for example, where rho is equal to 0, and then a similar equation for A, where rho and J are equal to 0. So away from the source, phi and A satisfy this dynamical equation, and that occurs so often we use a symbol square to represent that operator. It's called the D'Alembert. The D'Alembert is that combination of second time derivative and the Laplacian. And that's a very simple way to write the wave equation. Square acting on phi is 0, or square acting on A is 0. Or also, away from the source, square acting on E is 0, and square acting on B is 0. It's the same formalism, mathematically formally the same equation. Now this wave equation, so-called wave equation, there are actually lots of wave equations. This is if you just talk about the wave equation, this would be the simplest wave equation that you'll encounter. There are other wave equations. This is the wave equation for light in vacuum. And what we mean there is planar where there's nothing, no other impurities or matter present in the region. So no air, no glass, nothing, right? It's just the plana by itself. And as we saw for that, the motion of a form just simply travels. So any sort of solution is just taken by taking some shape and traveling it through. Okay. If you were looking at propagation of light through glass, for example, or water or any sort of transparent medium, or even through the air, this equation does not quite hold. There are differences. And you know, for example, if you propagate light through glass, that you get a dispersion of the colors. The colors break out. Or water through light through water does the same thing, hence the rainbow. You get that. So this equation does not contain that dispersion of the colors. The colors in this, in the light, God bless, traveling through this are not dispersed. They propagate together. So this is what's called a dispersionless wave equation, and all in the sense that all colors, all frequencies. I'm getting a little bit ahead of ourselves here by talking about frequencies and colors here, but anyway, just to give you some perspective here, this is called the dispersionless wave equation, and that, as I said, if we have phi looks like this at some time, then phi at a later time will be, if this is a right traveling wave, will simply propagate over to the right, and without, I'm running out of, not letting me draw over there. Anyway, it will simply have propagated over to the right or to the left, or some combination of motion to the left and right. Some part of this may be right traveling and some part may be left traveling. Okay, now so this wave equation, this dispersionless wave equation, is kind of like the simple harmonic oscillator of waves, in the sense that we had, when we took a mass on a spring and we considered that motion, and we saw that there was simple harmonic motion. It was very simple behavior. It was periodic motion, and we said that this kind of behavior is going to be seen lots of places. And we saw, for example, something like simple harmonic motion in an LC circuit. That is, that the charge on the capacitor, we got charge on a capacitor, and had it discharged through an inductor, that this thing would oscillate like a simple harmonic oscillator. So there was an analog between a mass on a spring and a charge in an LC circuit. So there's a mathematical, a formal analogy between them. And in fact, there are lots of places where the simple harmonic oscillator shows up in physics, because you have some kind of stable equilibrium. That is, the system wants to be stable in some state, and you change the state a little bit, then there is, in a stable system, a restoring force that tries to push the system back to the equilibrium. And then it will overshoot, and then there's a restoring force back in the opposite direction, so it oscillates. And so there's very generic behavior, the simple harmonic oscillator, in lots of different places that you'll find. The wave equation is kind of like that for waves. It's kind of like the simple harmonic oscillator. It's the ubiquitous behavior. You'll see it in lots of different places, or something like that. And in fact, you can get the wave equation by considering a set of oscillators. You could consider, for example, take a series of masses connected by springs. And hook them up like that in series, like this. And if you solve for the behavior of this system, you can get something that looks like a wave equation. In fact, if you take the limit that the masses, you break the masses up and put smaller springs between them, and you hook them together, that you can get to a limit that looks like a rubber band, for example. And the equation that describes the motion of the rubber band, the oscillations of the rubber band, is the wave equation. And you can see that. Suppose we take, in the case of the rubber band, let's say that we have y of x of t is the displacement of the rubber band perpendicular to the line. Then if we look at the force on a little section of this rubber band here, so the force will cause an acceleration, a y double dot, of that little piece. And the force comes from the curvature of the rubber band. That rubber band is curved, and that curvature, in this case, in that little particular section there, downward curvature. That's going to pull the rubber band down at that point. This point here, its upward curvature is going to pull the rubber band, that section, up. So there's a net force on this rubber band, on this section of the rubber band down here, and a net force that's up. And the force is proportional to the curvature. That is the second derivative of y with respect to x. And that's the wave equation. There you see y double dot with a factor of the speed minus y double prime. This is the wave equation in one dimension. So this wave equation is going to show up in a lot of places, or variations on the wave equation, and this is the simplest one. And so we can see it comes directly from Maxwell's equations once we have the dynamics of Maxwell's equation, but it's going to show up in lots and lots of different places. So this is, again, like the simple harmonic oscillator, is going to be a kind of prototype for this kind of behavior. And so a wave here, what we have in the wave, in the case of this rubber band, is an extended substance. It has extension, and it's some kind of coordinated motion. The waves show some kind of coordinated motion of the parts of the substance. That's what a wave is. It's doing something over here. Well, that's going to be related to what it's doing over here in some way at a different time. And so propagation is a way of saying that what's going on now is going to propagate. What's going on now here is going to propagate over here and influence what's going on. Okay. And so we saw, for example, to continue this kind of comparison, let's take the rubber band case, and let's suppose that we have the end of the rubber band like this, and so the rubber band is going off this way, and it has an end, and I'm going to shake. I'm just going to snap it once, like that. And what you would expect to see then is a hill in the rubber band is going to propagate that way, to the right. And that would be what we saw before, what I demonstrated before in last class. We get these propagating solutions from the wave equation. Okay, so that's now notice here, what happens in the rubber band is dependent on what's going on here on the end. If I take the end and shake it periodically like this, then what will happen? Well, that oscillation will propagate down the line. And so if I shake the end, I'll get an oscillatory motion that will propagate over to the right. So to illustrate that, switch over here to this, just for this one little animation. So that's an example of what it might look like, what the rubber band might look like if I'm shaking one end up and down, and it's going to propagate then to the right, away from the source, propagate into the rests, into the rubber band. That's what it would look like. Okay, now this is different than what we did before. We just had just one shake, and then it propagates. But now this is what characterizes this is periodic motion. This is a periodic behavior. It's periodic. Why? Yeah, because of the source, right? Me on the end is shaking it periodically. And that's what makes the solution periodic elsewhere. The periodicity, the wave-like behavior, comes from the source. Remember, because we said that we could get propagating through this medium in the rubber band through the wave equation, we could get any shape that would just propagate to the right. But what makes it periodic is the source. I'm shaking it periodic like this. Okay. So what causes that periodic behavior is the source. I'm shaking. So in this case, I'm shaking it up and down. In this case, this was just shake it down, up and down once, right? Hold it up, shake it down, and you get the single hump traveling. But if I continue to shake it like this, I'll get this wave. And that's because this part here, remember, was caused because at later time I was holding the rubber band up. And that's why these peaks are there. Okay, so now what is the characteristic of the behavior that I'm doing here? There's one, it's the period of motion, right? So the period of the motion of the oscillator, so there's a period here. The period of the motion of the source. And I could, another measure of the same thing is the frequency of the motion, 2 pi over the period. It's the frequency of the source. Okay, so now if I come over here to this point and watch what happens. At this point it's high, but then as the wave moves by, it comes down. And so I get a kind of mimicry. I get the same kind of oscillation over here, just over displaced at a different location. So I have the same period of the motion over here. The driver, which is me shaking this thing, I'm determining the periodicity of the motion elsewhere. It's going to have the same period somewhere else. It can't have a different period. So this periodicity in time is repeated in other places, and the propagation does it in such a way that the period of the motion is maintained everywhere. So everywhere, all along this place, the periodicity of the motion is repeated somewhere else. So let's go back over to this. You can see that again. Let's just look at, hello, it's catching up. Okay, let's look at just one location here on this and watch what it does. Okay, so it comes up, just pick say 5, and you can see it's sinusoidal motion at one location, and the period is the period that's determined by the driver over here on the right. Okay, so you have periodicity in time, and that's determined by the driver. Now I'm going to stop this though. We could take a snapshot in time though, and notice there's another kind of periodicity, which is related. And that's the periodicity in its relation along the extension here. We've got a peak, a peak, a peak, and there's a distance between the peaks. And that distance between the peaks is related to the frequency. If I up the frequency, I'd have less distance between the peaks. If I shake it faster, then I get less distance between the peaks. Does that make sense? So the other thing that characterizes this behavior is the wavelength, which is the distance between in the periodicity between the crests. And just like there is this wavelength, we have this thing called wave number, which is 2 pi over the wavelength. This is called wave number. So the period and the wavelength are related to each other in the same way. If I inversely, it's easier to talk about frequency. If I increase the frequency, I get a shorter wavelength. So what's the relationship between the wavelength and the frequency? Well, it has obviously something to do with the speed at which this wave is moving. Right? If the speed propagates quickly, then I'll get a long distance between the crests. So we said this, that the wavelength is going to increase with the speed. And how is it going to depend on the frequency? If I increase the frequency, does the wavelength go up or down? It goes down, right? So in fact, there is this relationship, omega lambda is c. There's 2 pi in there. I'm sorry, excuse me a second. There's a 2 pi I've got to put in here. This must be on the right-hand side here, 2 pi. Yeah, right, there's a factor of 2 pi. If you figure out here that the cycle has to go through 2 pi, omega is an angular frequency. So there's 2 different frequencies that we talk about, nu and omega. Omega is an angular frequency, and nu is just a frequency. And so when you hear a frequency, you have to ask, is this an angular frequency or not an angular frequency that we're talking about? So nu is just 1 over the period, whereas omega is 2 pi over the period. They differ by a factor of 2 pi. So this is called angular frequency. Okay, writing this in terms of k and omega, this is what I was coming to here. The relationship between the frequency and the wavelength is usually written in that fashion. Omega is equal to kc here. So if you fix, omega is fixed by the source, and lambda is then determined, so you could write it as ct, right? It's the distance traveled by the wave in one period. That's another way of saying it. How long does it take, how far does it go in one shape? Well, that depends on how fast it's traveling, and the speed is c. And so there's a relationship between the wavelength and the frequency, the period of motion. That's determined by the source. Frequency is fixed by the source. The wavelength is a property, is a combination of the frequency and a property of the plana, in this case, the property of the medium. The speed of propagation is a property of the medium. The wavelength is determined by the frequency of the driver and the speed of propagation. So it's a combination of what's driving it and the medium that it's being propagating through. In the case of light, it's plana. Okay, so let's go see what would happen now. Let's imagine we have an antenna. I'm going to put a piece of metal here. I don't want arrows on it. I'm just going to put a piece of metal here. And I'm going to have charge moving up and down on this some way. Hook it up to an AC voltage source and drive current up and down through this thing. So we have charge is distributed, say, crudely speaking, without being very detailed at this moment. Maybe we get plus on one end and minus on the other end, and then we oscillate. We switch it back the other way. So it would oscillate like this, for example. So we'd have charge swishing around on the metal antenna, and we want the period of that motion, t, determines the frequency of that antenna, the dipole antenna, is just that. So now we're going to get associated with that, of course, a phi field. Because remember, there's a phi field that's associated with a dipole. The dipole generates a phi field, but now this phi field keeps flipping because the dipole keeps flipping. Now that's a little harder actually to draw, so I'm going to draw something that's a little bit easier. Let's think about this. Associated with this, we have a current flowing. We could have a current that flows up and down like this. Okay, and now we have a period of motion, right? We have current going up, current going down, current going up. Now let's look at the A field that's generated by this. This is going to be a little easier to draw. We could work with the phi field, but the A field is a little bit easier to draw here. And actually, fundamentally, physically, radiation is dependent on the A field. Okay, so let's see what happens. We have the current's in this direction, so what is the A field doing in the vicinity of the antenna? It's up, right? So the A field looks like that. Okay, and now we, over time, let's suppose we switch the current down. In half a period, it's now down, and the A field right adjacent to the antenna is going to be down. So this is the A field. But farther away, was up, right? Because this A field here, in this case, is propagating outward with the speed of light. And so this distance here is going to be c times the period over 2. Where this period now, the time is half a period. Okay, and then now after another half period, the current in the wire is up, which means now the A field is going to be up and very close to the wire. It's going to be down here and then back up here, and so this distance, lambda, will be c times the period of the motion, And so the A field is going to be sinusoidal, like that. Okay, so what we want to look at there is, I want to describe that in a mathematical form. What does the A field look like? And I'm going to do this in 2 dimensions, x, y, and I also want time. And in fact, I'm only going to look at the A field for the purposes of this point, where we're just examining things. I want to look at the A field along the x-axis and not get farther off. So let's just look perpendicular to the dipole antenna, just to make it understand it simply. Okay, so what is the direction of the A field? What is the direction that the A field points in? Not the direction of propagation. Yeah, the A field is pointing in the y direction everywhere. Sometimes up, sometimes positive y, sometimes negative y, but it's only has components in the y direction. And it has an amplitude, which depends on the magnitude of the current. And then it has a behavior which looks like this. I'm going to write it cos kx minus omega t. And remember, k is 2 pi over lambda, omega is 2 pi over the period, so you could write this in a little bit less compact notation, 2 pi x over lambda minus t over the period. That's another way of doing it. Maybe a little more clearly relates it to lambda and to the wavelength and the period, but it's a little bit more compact to write it in terms of wave number and frequency. Now this fits what we had before. Remember, if omega is kc, then this form, k cosine kx minus omega t, we can factor out a k from the piece inside here, k x minus ct. It's another way of writing it. And that's, you recognize that. Remember, we said that was a generic solution to the wave equation. It was anything propagating to the right is a solution to the wave equation, right? How do we know that this propagates to the right? Let's set the argument of the cosine equal to a constant, say 0, for example. So kx minus omega t equals to 0. That's where the cosine is a maximum. Well, then x is equal to omega over kt, and omega must be proportional to k. K must be proportional to omega. So this is traveling to the right. Now there's another wave that's traveling to the other side of the antenna that would be a left-bound wave, right? And we would describe that one, God bless, by switching the sign here on the argument of the cosine. The left-bound wave on the other side of the antenna would be cosine kx plus omega t. That's a left-bound wave. It's going off to the left. Okay, so that's actually, you're going to demonstrate in your homework that that's a solution to the wave equation. But let's investigate the behavior of this thing, this A field here a little bit. Let's start with this. Let's take this thing here. So that's a right traveling wave. It's the A field that would be generated by an oscillating current and a dipole oriented in the y direction, and the direction of propagation is to the right. Now notice again, like we've often found, the direction of the vector is perpendicular to the direction of propagation, right? Those are different things. Okay, so let's start with that. Let's look at this wave, at this solution. So this characterizes the A field in the plane C, generated by an antenna oscillating with frequency omega, and K is omega over C. right? So omega is fixed by the source. And the wavelength is determined by the medium as a result of fixing the source. Okay, so now we have an A field. Well, let's look at different parts of the A field. As a result, the A field has both an E and a B, right? The Maxwell E comes from the A dot effect. So there's going to be a piece that's an A dot, and there's also going to be a curl to this. So let's look at the curl first, because I've drawn the wave here. You can see that there's a curl. Let me go ahead and draw it out here. Okay, so we have an A field that's looking like this. Okay, so this being along the x direction, like that. Okay, let's look at the curl, the B field. Which direction is the curl going to be in? Well, it depends on where you are here. So let's look right here, right at the beginning here, where I start drawing the arrows in this region. Which direction is the curl? Into the board. So there's a B field in this direction. So we have our coordinate system x, y, and then z comes out. In this region, B is going to be in the negative z hat direction. And how about in this region? It's still into the board. Still into the board. Right at this place here, is there a curl? Right at that location. Now, where the A is a maximum, there's no curl, because the derivative of A with respect to x is 0, because A is a maximum or minimum. Okay, now on the other side, then B is coming out. In fact, there's a maximum B here and a maximum B into the page here. So B is oscillating, and we would get it just by evaluating the curl of that A field. And it oscillates, and it's in the z hat direction. So we get an oscillating B field. Well, that makes sense. Remember, go back to the wire that's making this thing. The current is going up and then down, and then up and then down. And if you look at the B field, that should, well, in one case it's going in one direction, and we change the current, it goes in the other direction, or this way, right? So if we change the current, the direction of B is going to change. Change the direction of I, the direction of B will switch. So B is oscillating back and forth because the antenna is doing that. And we also have, we should look at the grad phi term, but I'm going to do that separately. I'm going to focus on the dAdt piece, and the trick would be to try to construct an antenna maybe that doesn't generate a phi. It's a little tricky. But let's just focus for now on just the A dot piece. Okay, and the A dot would be, you look, remember, at the location where the plana is, what is the A field doing at that point? So where the do this thing again. Okay, so remember, this wave in which direction? To the right. It's propagating to the right. So you want to pick a location and then kind of figure, because of the propagation of this wave through it, what is happening to the A field at that location. So right at this point, A is a maximum, right? So the E is going to be 0 here. There's going to be no E field. But right here, the E field is increasing. In fact, this is the biggest change in A. And which way is A going? It's going down, so the E field is here, in that direction. The E field is in the Y direction, and it's a maximum here. Again, it's back to 0 here, and now coming back over to this place, the A in the center here. The A field is increasing, so E is in the opposite direction. Okay, so the E field is going to have this shape to it. Oops, add interpolation there. Okay, so the E field is, as you can see, you can imagine, just take the time derivative of that cosine, E field is going to have sinusoidal behavior as well. But notice that the, let's see here, yeah, the maximum E field and the maximum B field are at the same place. So we had the maximum here and a maximum here. We have 0 B field here because the field is symmetric, so there's no curl there. So there's a 0 in the B field here, a 0 in the B field here, there's a 0 in the E field, 0 in the E field. So the zeros in the E and B occur at the same place. The maxima and minima occur at the same place and time. So they're synchronized. Okay, now it's not surprising to look, as we said, I want to re-emphasize this, is not at all surprising. The E field does in fact relate, the curl of the E field does in fact relate to the time derivative of the B field. This is one of Maxwell's equations. And away from the source, there should be a corresponding relationship between the time derivative of E and the curl of B. These hold. But why do these hold? Well, E and B are both caused by the source. We calculated it through A, so remember we did this through A. So they're both caused, they have the same cause. And so they're correlated with each other. And that correlation comes about because they come from the same source. So these equations do not hold in them causal relation. It's a correlation, but not a causal relation. And that's the thing to remember. And by sketching it out here, as I just did with this, I think you can see how that comes about. Because these fields just propagate outward from the source. So there's nothing very mysterious about it. It's really pretty simple. Okay, so now, and also A and phi satisfy equations like this. We saw A, and there's a similar equation for phi. There's a general solution that he shows you here. Phi at some location and some time can be determined by integrating over the source the charge density at some location R prime is the influence is weakened by 1 over the distance between those two places. If I have the source is here at R prime and I want to know what phi is over here, then I have to know the distance between them, and in fact it's weakened by that 1 over the distance. But now we have to take into account the propagation here. Previously we just left it at this. The rho was not changing in time and phi was not changing in time. When we had electrostatics, we didn't allow charges to move. And so this was it. Now what we have to do is to take into account what's called the retardation. And so we have to figure what is the charge density doing at a location at a time earlier. You know, when we look up at the light coming from the stars, we're seeing the stars, of course, the light that started on the journey years earlier, maybe millions or billions of years earlier if you're looking at a faraway source. That retardation in time has to be taken into account. It's what the source was doing back then. And so that retarded time is now the time we want to know phi. Earlier, by the amount of time it takes for the light to travel that distance. And so that retarded time has to be taken into account in the integral. Carrying that integral out is a little challenging. All right, this is in order to do that, you have to be careful and you have to do the integral carefully, and it makes it a little more complicated. But physically, it's quite simple. You're just taking into account the delay. Different parts of the source are going to have a different delay because they're at different distances from the location where you are. Right? If I have a source like this, and I want to know what the phi is doing here, and rho is moving, sloshing around inside there, well, the nearest pieces are going to have shorter propagation time than the farthest pieces. And so phi here is going to be influenced differently by the different parts because of that. Right? You have to take that into account. So this is called the retarded potential. And it simply takes into account the propagation of the field through the plana. And there's a similar one for the A field. Well, actually, before I do the A field, let's look at this one. This is what we looked like before. If we set C to infinity, then that time delay becomes negligible. If C is effectively infinite, then we can drop that delay, and we're simply looking at how the source generates the field over here without any consideration of propagation. And that's okay if you're dealing with small enough distances, God bless, and the changes in the source are slow enough that you don't have to worry about the propagation. So that's what we were doing before in electrostatics. So that goes back to the electrostatic solution as we got before. The A field, remember, it was the integral of the charge current density. And again, we want to know the A field at a given time. Well, we have to take into account the retardation, the propagation time, and so it's just exactly the same. And that's what we did when I was sketching the solution up here. When we did this drawing that I made here showing what the A field is doing is just doing that. I'm just taking into account the propagation, and so that's really all that's contained in this. And before we had the static case, when we did magnetostatics, we said we didn't want the current changing. So the propagation wasn't relevant because it had been there for a long time. Things weren't changing, and so we could neglect that delay, that retardation. So that we had this equation in the magnetostatics chapter where we neglected the retardation. Okay, so now we're getting into the fully dynamical thing, and that's really what the dynamics comes in, is simply the dynamics of the plana, so to speak, is the response of the plana to a source, a changing source. And that's simply the propagation. It's really not complicated in that sense. It may be a little difficult to calculate, but in principle, the physics of it is not that complicated, right? It's easy to understand. Okay, any questions? Yes, sir. Mr. Bacot.
Why is it a triple integral?
It's because it's a volume integral. It's integral over a volume.
So, like, the source would be a volume?
Yeah, that's right.
Okay.
Yeah. It's a volume density, both a volume charge density rho and a volume current density. So the source is three-dimensional. Now, you could specialize that. In the case of the antenna, you could limit it down to just a one-dimensional integral.
Just the way you were drawing, I was thinking of like a wire going around.
Oh, excuse me. That's not a wire. Yeah, this is a potato with charges running around inside, right? Cooking it. Okay. Other questions? No? Okay, so that's it for today. Then what I'm going to do is pass out your homework.